Mentioned about some special function called Euler phi function. Euler phi function is counting the number of numbers or positive integers satisfying two conditions. The number inside this set should be between 1 and n, right? The number should be already set positive, so I don't even need this side, but let's be specific. And the second condition is GCD condition. GCD of the number inside this set and the given number n should be equal to 1. Any questions about the definition? So last time we calculated phi of many things. For instance, phi of 5 is the number of numbers satisfying the condition, and then as you can see, 1 satisfies both conditions, 2 or so, 3 or so, 4, but not 5. So there are 4 numbers here, so the answer is 4. And if we have phi of, for instance, 9, then the number of numbers satisfying this condition, 1, 2, 3 cannot satisfy, 4, 5, 6 cannot satisfy, 7, 8. So there are total 6 numbers. So we browsed many cases. And this has some properties. And first of all, if P is prime, then except P itself, all other numbers have GCD equal to what? 1, right? Because there are no other divisors dividing P, so GCD should be 1 for all numbers but P, so it is P minus 1. If you have a question about this, ask me. Then the next thing that we considered was P to the power of K, then it is P to the power of K minus P to the power of K minus 1, or you can write it this way, P to the power of K, and then 1 minus 1 over P. And one more thing that we found was phi of n is even if n is greater than 2, right? When n is equal to 1 or 2, it is 1. But other than smaller 2 numbers, phi of n is even. Of course, today I will prove this thing. But there is a very, very important property that we can consider. That is called the multiplicity. The function here is multiplicative. In other words, phi of m times n equals phi of m multiplied by phi of n if GCD equals what? 1. So this is the one that we will prove today. But before proving it, I want to make sure that you know the definition clearly or not. So for instance, take a look at, is it too small? So I will magnify it. So take a look. If f is multiplicative, then f of 8 multiplied by 16 inside the argument position is f of 8 times 16. Is this correct or not? Yes or no? Just yes or no? No, why not?
Because it's a general function. There's no conditions associated with the GCD.
I mean, I said f is you said GCD, right? So f is multiplicative, then is true or false? That is the question, and he said no, and answer is right. His answer is right. Why? Because the function is multiplicative doesn't mean we can just multiply 2 cases. No. Only when GCD is 1, we can multiply. In this case, what is the GCD? 8. 8 is not 1, so it is wrong, right? Do you understand what I mean? In other words, you cannot say this thing. Oh, if function is multiplicative, then if function is multiplicative, then you may say, oh, phi of 9 equals phi of 3 times 3 equals phi of 3 times phi of 3, and then phi of 3 equals like 2, and then 2, and then 4. And then this is not correct. Do you see it? You cannot say this. Why not? Because the GCD of two numbers is not 1, right? The GCD should be 1. To be multiplicative, it should satisfy this condition only when GCD is 1. But unfortunately, it's not, it doesn't satisfy the condition. So even if phi is multiplicative, there is no rule like this. Some function may have this kind of rule, but generally multiplicative function doesn't have this kind of rule. Do you follow me or not? If you don't understand, you can ask. So in this sense, when you have, for instance, phi of 2 times 2 times 2 times 3, you cannot say, oh, phi of 2 multiply phi of 2. You cannot say this. Do you understand what I mean? You cannot say that this is true, right? This is not true. Why not? Because these 2's have GCD equal to 2, not 1, right? So we should collect these kind of terms, and if we really want to split, then we should split this way. 2 to the power of 3, right? 8, and then 3. We should split this way. Then, because GCD of 8 and 3 is 1, we can write it this way. Do you see it? Then, after this, you can use the factor that I mentioned upstairs. When you have phi of p to the power of k, then phi to the power of k minus p to the power of k minus 1. So in this case, phi of 2 to the power of 3, so it is what? 2 to the power of 3 minus 2 to the power of 2. And then in this case, 3 to the power of 1 minus 3 to the power of 0, or 3 minus 1. And then if we calculate this thing, then 8 minus 4, 4, and then 3 minus 1, 2, so 8. 8 is the answer. Any questions? Then let's verify these things using computer algebra system called MATLAB. And it is phi of, for instance, 24, 8, right? Phi of 8, 4, phi of 3, 2. 4 times 2 is 8. Now you may pick any number. What number do you want? A is equal to what? 27. And then B is equal to what? 52. Then let's count the GCD. Let's calculate GCD is 1. So let's do this calculation. Phi of A multiplied by B, and it is this one, right? Phi of A is what? I will call this number AP, right? AP is phi of A, and then it is this number. BP is phi of B. Then AP multiplied by BP. The same number, right? So we have the multiplicity satisfy phi. But unfortunately, this is not a course just covering experiment. It is a course requiring proofs. So we need a proof that this is multiplicative. So very important theorem is this theorem. Phi is multiplicative. And as I mentioned, this will be questioned on the following exams until final exam. In other words, once you know, you may solve this time, next time, wherever. If you do not study this time, then you will get bad score, and then next time you may need to restudy. So try to master it right now. So before proving it, I will prove a thing that I already proved before. You may remember this thing. If GCD of AC is 1, and then GCD of BC is 1, then from this thing we can get GCD of AB, C equal to 1. You may remember this thing. Using this, I solved A to the power of n and B to the power of n case GCD, right? And I will reprove it so that you can understand it. I already proved, but I will prove both directions. First of all, the other direction is easier. If GCD is this one, then A, B, C, and then 1 satisfies some mathematical relation. What is it? A times B, and then C satisfies some mathematical relation. What is it? Some number, XY. Some integers, XY exist, right? This is the very, very important property that you should remember, right? When GCD equals something, then you can represent the GCD using this kind of linear combination. Now, if we exclude B part, then we can call this nu x, right? So it means AX plus CY equals 1. It means if we convert back, we converted this statement to this one. But if we convert back to the same statement, same kind of statement, then GCD of what? AC equals what? 1. Do you follow me or not? If you don't, then ask me. So it is the GCD statement, right? GCD becomes mathematical expression, right? Not concept expression, mathematical expression. And then this mathematical expression represents the GCD, concept expression. In any case, I proved this one. And the same way, we can prove that using BAX plus CY equals 1. We can say that GCD of BC equals 1. So it's very trivial direction. It's already there. This expression, you can do it. And the other direction, I already proved that you can find about a month ago maybe. The other direction will be proved unless you have any question. The other direction. Because of this, AX1, CY1 equals 1. Because of this, BX1 plus CYX2, CX2, CY2 equals 1. Then multiply both sides. You may remember this now, right? Then AB, X1, X2, and then, as you can see, all other things. AX1, Y2 multiplied by C, and the other multiplication, C, and then B, Y1, X2, and then this C, C, Y1, Y2 equals 1. Then as you can see, we can extract these things. We can extract AB, C, and then because of this, GCD of AB, C is 1, right? So it is nothing but the conversion between concept expression to mathematical expression, right? Mathematical expression to concept, and concept to mathematics. So I gave the proof before, but this is the second time. If you have a question, you can ask me. In any case, when you have product GCD equal to 1, when you have product GCD equal to 1, then individual GCD is also 1. Yes?
So we did this proof on the test. We have to prove this part also, or can we just assume this part's true?
Yeah, I will specify. I will specify. Any other questions? Then using this thing, I will begin to prove. So I will use a new column. The idea is very simple. We need to find, so I will write the definition one more time. If GCD of M and N, GCD of M and N equals if the GCD of the number and then M and N equals 1, right? If this happens, and then GCD of the given number M should be 1, and GCD of the, so regard this as C, N equals 1. Do you follow me? So if this, in other words, we are counting the number satisfying this condition, right? By definition, phi function counts the possible number of these boxes, right? 1 through M and N. So we are counting it, but instead of counting the product, we are just counting for each individual element. So this is the situation. But I felt that before going into abstract proof, it might be a very good idea to really touch it using actual case. So I will use MATLAB to produce something that we can use. So you may pick two relatively prime numbers. Any set is okay. But just a moment, before using MATLAB, I will use very easy case to show you the fact. 2 and 3. Then 2 times 3 gives us total 6 numbers. So I will write number in this way. 1, 2, 3, 4, 5, 6. And one numbers are relatively prime to 6. 1 is relatively prime to 6. 2 isn't. 3 isn't. 4 isn't. 5 is, right? 5 is right. 6 isn't. So there are 2 numbers. So do you follow me? But if you see a small sample, then you don't get the big picture. So please pick moderately big numbers, like about around 10. Then I will create this kind of table and then count the number of numbers having this satisfying this condition. So please pick 2 numbers. I didn't make up the number. You chose 2 numbers, about around 10. 2 numbers. 11, and then what? And then 8. 11 and 8. This is not my choice. It's your choice, right? So let's do it. So 11 times 8, right? So I will create the list from 1 through 11 to 8. And then I will make it 11 by 8 matrix. So I created this matrix, 1 through 88. Instead of writing down all the numbers, I created this thing. But I didn't make this up. You chose 8, 11, and 8. I just commanded and then create this thing. Then let's take a snapshot of this thing and then continue. This is it. So take a snapshot of this thing and then write it, locate it here. So these are the things that we will use. Unless you have a question, I will continue. So let's do it. First of all, 1 is relatively prime. So I will just use marker to count, right? So, I will exclude. Sorry, I didn't transpose the matrix. It's not wide enough. Maybe this is okay. It doesn't matter. Any order I could write, right? In any case, so let's just count. First of all, with respect to 11, I will cancel out. First of all, 11 is prime, right? So only thing that cannot be counted is this row. Do you follow me? Or a column, right? You can regard this as a transposed matrix. In any case, these are disqualified because it's the multiple of 11. Now, multiple of 11 is all gone. Do you see any more multiple of 11? No, right? Then now it's time to eliminate any number which has GCD greater than 1 with 8. In other words, any multiple of 2. Any multiple of 2 will be eliminated. This 8 was not chosen by me. In any case, you can remove any multiple of 2. So multiple of 2 are all gone, right? So I am just extracting multiple of 2. And in fact, this is the strategy that I will use to prove generally. But once you see, you may get an idea. So initially, I used either row or column to disqualify one big column or row, right? One or more than one big row or column. And then afterwards, I handled individual, in this case, columns, right? In each column, how many can you count? In each column, how many can you count? 5. And then how many do you, count means, yes, 5 is correct, sorry. Yeah, both way, right? This both way. And 5 times, how many total rows?
8.
8. 5 times 8. That is 40, right? So after this calculation, we guess the answer could be 40, right? Any objection? This is the strategy that we will use to prove general case. So I will rephrase it. How many rows were qualified in the first step? How many rows were qualified in the first step?
11 minus 1.
Right, 11 minus 10 rows were qualified, right? Only one row was disqualified, right? So marked one is disqualified one, right? Only one row was disqualified. It means 10. 10 is phi of what? Phi of 11, right? 10 is phi of 11. Now, how many entries in the column are qualified? 5, right? So, oh, I think something is wrong here. Why you mentioned how many rows were disqualified? 10. And then I made a mistake right here, right? 40 was wrong, 50. Right? Some miscalculation, right? There are 10 rows, and then in each row, right? Is it? No. I'm completely confused. Sorry for the mistake. 40 is correct. Yeah, you may see it, I cannot see it. let's we mention it. First of all, in each row, there are 10 rows, 11 rows. Among 11 rows, P of phi of 11, which is 10. So my brain is malfunctioning. I cannot think clearly, but this is the idea. We have total 10. 10 is that was the mistake. 10 rows should not even counted. That is like columns, right? Total we have 8 columns. 5 times 8 columns, right? 5 times 8 columns.
10 rows times 4. There's 4 in a row.
4 in a row? I see. Yeah. That one is the one, right? That one is right. So you are right. I was because I was initially trying to use row and column. After switching row and column, suddenly my brain cannot adjust. So this is correct statement. Here we have phi of 10, and phi of 11, which is 10 qualified rows, right? And then in each row, we can find 4 qualified entries. No, 4. Is it 4? Yes, 4. I'm completely confused because it gave the same result on the column side. That's the reason why I was confused. But in fact, we should calculate in 2 different ways. One way in column, the other way in row. In other words, in this direction, phi of 8, which is 4, right? Phi of 8 is 4. Do you see? So please check it. I myself had a very hard time. First of all, it was switched, and second, it has same number of entries in this column or row calculation. That was the reason I was confused. So it is 4 times 10 cases. So we showed this using an example. Do you need more examples, or this is enough? More examples is okay if you want. Let's use 10 by 7. That might be a little bit manageable. 10 by 7 is still large. 9 by 7 might be good. Or m equals 8 by 7 might be good enough, right? 8 by 7 I will use. One more time. Let's try. So I will redeem myself. 8, 7, and then reshape the matrix 1 through n multiplied by m times n, and then it is 7 by a matrix, but I will transpose it. Phew. This was the one that I intended initially. Even this way, A7. Yeah, A7 might be better. But it could be too wide or not. So I will use this thing to re-show you the case. But in this time, I will use column counting first instead of row counting, because I practiced that way, and then I come here and then use the other way. Oh. So this is the case that we want to consider. First of all, let's disqualify in the disqualify some columns. First of all, with respect to 8, 8 multiple is disqualified, right? Do you see it? And then this multiple of, right, these things are disqualified. If you don't agree with me, you can stop me. With respect to 8, I disqualified these big columns. Then we can only focus on rows. Now with respect to 7, this is disqualified. 14 is disqualified. 21 is disqualified. 28 is disqualified. 35, 42, 49, and then 56, right? So these are disqualified. Then, as you can see, in this direction, we see total 4 entries, right? 4 entries. In this direction, generally, in each column, how many do you see? 6. Pick any column. In this column, 6. In this column, 6. 6, 6, right? So this is the idea to prove the case. So after this, I will now begin to prove it. So let's do it. One through m, and then the next number m plus 1, and then m plus 2, m plus 3 up to m plus m, that is 2m, right? And then 2m plus 1, and then 3m, and then all the way up to m times n, right? M times n, or n times n is also okay, right? 1m, 2m, 3m, and then nm, and then m minus 1, m plus 1. And we can write the numbers in this pattern, right? 1 to 3 up to this thing, and these are written. So take a look. Assume that some x exists, or let's use r. Some r exists here. Then this number is m plus r. This number is 2m plus r, and so on up to n minus 1 m plus r. Do you follow me or not? If you don't, I will be slow. I will slow down and read. So let's consider GCD. GCD of R and M, right? We only care about this direction. GCD of R and M equals GCD of any entry here. So let's say Km plus R and M. If you don't agree with me, you can ask me. Because the quotient, if you divide this number by n, the quotient is k, remainder is r. Do you remember Euclidean algorithm or division algorithm? Euclidean algorithm is possible because once you have this thing, if you divide this number by m, then we can just take the remainder to have the same GCD, right? You understand or you recognize this thing? In Euclidean algorithm, you used it, right? You used this algorithm in Euclidean algorithm, right? If you divide this number by m, the remainder is r, then the GCD is the same, right? GCD of this number and the remainder should be the same. Because of this reason, if this is disqualified, all the numbers below is disqualified. If this number is qualified, then all the numbers below will be qualified. Do you follow me? In other words, if something is qualified, then all the numbers below will be qualified. If this is not qualified, then all the numbers down will be disqualified. In this sense, as I did before, you can just strike out whole columns or keep whole columns. It cannot be picked in column, right? Do you follow me? So this is the first step. Then in this region, how many can you count? How many numbers can be qualified in this first top m numbers? How many numbers have GCD equal to 1? 1 through m, how many numbers have GCD equal to 1? No. By definition, for general m, the number of numbers satisfying GCD equal to 1 is what? P of m, right? By definition. Do you follow me or not? This is abstract proof. It's not actual number handling, only abstract handling, right? So in this column, we have phi m numbers. By definition, right? So number between 1 through m, there are pm numbers satisfying two conditions. Right? I wrote down two box conditions, right? Two box conditions is pm numbers. Now let's count the qualifying numbers in each column. So let's pick the case like this, right? So generic just column is chosen, right? Assume that this column is also qualified. We don't know what may be qualified in general, but assume that this is qualified. Then, among these things, how many can you disqualify? So I will do this thing. GCD of, I will consider just this set. R, m plus r, 2m plus r, and then all the way up to m n minus 1 m plus r. This is just one column, generic column with r. R is not fixed. R could be anything. R could be 2, R could be 1, and so on, right? Do you follow me? R could be 1, R could be 2 or something. But I cannot specify because it's general proof. It's not just a specific case. Then what I want to do is this thing. This one is essentially, first of all, how many numbers total can you count in this case? Total number of numbers in this set is what? From 0 to n minus 1. So how many numbers? N numbers, right? So the number in this total set is n, right? There are n numbers. Then the only thing remaining here is this. I will say that if we rearrange these things, it is nothing but 1 through n, mod n. So this is what I will prove. If you don't understand, ask me. What I will do is this. R, m plus r, 2m plus n, all the way up to that, has total n numbers. Among these n numbers, how many can you count generally by theory? Phi of n, right? That is it. But to do it, what should I show? I should show that these numbers are rearrangement of 1 through n mod n. That's the only remaining thing. Then, because this mod and this are the same, essentially, in this set, by definition, how many numbers are qualified in this set? How many numbers satisfy GCD condition? P of n, right? If you don't understand, ask me. So in this set, P of n is qualified. So before proving this relation, I'm mentioning about the goal. Our goal is proving that this set has P of n numbers qualifying the condition. But if you don't understand, ask me. So this is the step. So once I prove that this covers the whole set from 1 through n, then we are done. Because I pick generic column. It's not specified, right? R could be 1, R could 2, R could be 3, R could be anything, right? I pick generic R. For this generic R, it satisfies this kind of relation, right? This set is nothing but this set mod n. Then inside this set, how many numbers can you count? Phi of n. This generic column, meaning for any column we can do this thing. For any qualified column we can do these things, right? For any qualified column. So essentially that's the end of the proof. So only thing remaining is showing that the set given here having total n numbers is nothing but 1 through n. That's the only remaining. So to do it, what I will do is using pushing. When you have n numbers and then downstairs n numbers, then if each number occupies just one position, then it will spread all over through to this set, right? If something goes at the same position, then it cannot happen. Do you follow me or not? So this is the technique. A little bit advanced technique, but it's not very difficult to get, right? Assume that there are 35 students outside and exactly 35 seats. If 2 persons do not occupy one seat, then they can spread all over and then occupy the whole seat. The same idea, right? So the only thing to prove this thing is showing that this does not happen. This does not happen, right? If I show that this does not happen, then it proves that this set and this set are equivalent, right? That means to count the qualified number in the set, given set, is the same as to count the number of qualified in this set, and then in this set we have phi n number. Then by the first step, we disqualified unnecessary columns, right? And then in each column we also disqualified unnecessary things. But in each column, there are same number of numbers qualified or disqualified in each column, right? So please browse the idea and ask questions. So the only thing remaining is showing that 2 students do not occupy one seat. Then let's do it. So assume that here I have 0 m plus r, 1 m plus 1, 2 m. So generally I can say j m plus r is the center, right? Here j m plus r. And then I may pick another one. For instance, gm. G is used for G series, so I will pick a different letter. LM, sorry, I will pick another number. IM plus R. So I pick 2 different numbers because I attached 2 different numbers, right? Between 0 through n minus 1, I picked just 2. And then assume that they occupy the same number. They occupy the same seat. Then I will prove that these 2 students are essentially the same student, right? That's what I do. Then it's done. So let's do it. So if this happens, then Jm is equal to Im. We can subtract R from both sides, right? Or let's say with mod n, right? With mod m, we can say this thing, right? Oh, mod n. Here mod n, sorry. This mod n. If If you don't follow me, you can stop me anytime, right? With mod n, because we are counting with mod n. With mod n, these are equal, right? With mod n, these are equal. Then we can say that we can subtract r from both sides to get this thing. Now, I will use the cancellation law. By the cancellation law, I will cancel out the common factor. And what is the common factor? M. So by cancellation law, I can say J is congruent to I mod what? By cancellation law, N over G, right? Do you see? This is cancellation law. When I cancel some number, I should change the mod, right? Mod should be changed. And with this, G is what? Can you clarify G? G equals what? G equals GCD of M and N, right? By condition, GCD of M and N is what? 1. So, because of this reason, J is congruent to I mod N. But there are only how many possible numbers in between? Total N numbers. And they have the same congruence, meaning they are same, right? They are the same, right? J is I. So once I see one position and assume 2 students, then in fact it's not 2 students, it's 1 student, right? So this proves that there is no chance that 2 students occupy one position. It means there are 35 students outside, there are 35 exact seats, then each people occupy one seat. That means it completely fill the seats. No matter what column, I didn't specify the column, I just picked random column. Among many columns, I just picked random column, random qualified column, then it satisfies this condition, and then essentially I proved it. Because of this reason, the number of qualified, I will describe it. The number of qualified boxes inside the set are R plus M plus R, M plus R, 2M plus R, all the way up to M minus 1 M plus R is equal to the number of qualified boxes, right? Boxes inside 1 through N. Then, by definition, the number of qualified boxes inside N is called phi of N. So in the first step, I disqualified many columns. In other words, I picked qualified columns. Now, I investigate each column and then found qualified boxes. And then these qualified boxes are uniformly distributed. Right? Uniformly distributed. So this is the end of the proof. And please browse the proof and then ask questions. Because of this reason, because of the above 2 reasons, phi of Mn equals, initially we did number of qualified columns, right? It equals the number of qualified columns multiplied by the number of qualified boxes in each column, right? And then this gives us phi of M and then phi of N. So I completely proved it. So mystery revealed, right? It's completely proved. Very brilliant proof developed. So you saw 2 actual examples, and then maybe 3, right? I gave you a very small example before. But small example doesn't give you any clue. So I gave you bigger examples, 2 bigger examples. After seeing 2 bigger examples, you understand the direction, and then I completely proved this thing using this side. So I will pause, and you may check, because by doing this, you get at least 20% on the exam, right? On the next and final exam. So please check it, and then ask question if you have any doubt or difficulties. Now, because this is proved, we can do many things, really many things. Why? Without this property, we need to really count. We need to really count the numbers. But with this property, all we need to carry is factoring the given argument, and then after factoring it, we can consider prime powers, only prime powers. Then we can. And using this idea, I create my own algorithm to calculate phi. So I will briefly show you my phi function. So as you can see, I will open phi function that I created. And you can download these functions from my website. And as you can see, what I did was factoring, doing the factorization and then arranging it, and then I used the multiplicity. Using the multiplicity, I did this. So you can later browse the idea and then. So I will emphasize this one more time and then begin to use this property all the time. So emphasize this thing. Phi of pk is enough. I said enough, and then I'm writing different. So when you are asked to solve something, remember, it's because it's multiplicative, you can use phi of pk. So one thing that I want to prove is this thing. Oh, if you add phi of d for all divisors of n, then it is n. Prove it. So this is the question. Wow, it's tough. It's tough. How can I prove it? Then remember what? Function is multiplicative, right? So you don't have to worry about general n. So all you need to worry about is not this number, right? What should you use instead of n? What should you use? P to the power of k here, right? And then you need to show the p to the power of k. So all you need to do is this thing. And then mention about this property. Because p is multiplicative and p of k equals sum of this thing, it is true. Something like this is possible. I will show you this kind of thing in the future. But before going to the complex thing, I will prove an easy fact. Prove an easy fact. If n is greater than 2, then phi of n is even. This is the one that I want to prove first. So n can be factorized. N can be factorized by this thing. 2 to the power of, for instance, if n is even, if n is even, do I need this thing? Just n is, and I will use this, right? I will use this. If n is purely 2 to the power of some k, where k is greater than 1, because if k is exactly 1, then it is not true, because n is greater than 2, and this k cannot be exactly 1. Do you follow me or not? So it's not possible, right? If this happens, so proof, if this happens, then phi of 2k equals 2 to the power of k minus 2 to the power of k minus 1. And then we can extract the common factor 2 to the power of k minus 1. Then the remaining thing is 2 minus 1, and then 2 to the power of k minus 1. And then, because of this condition, this is even. So I proved it. So if, for instance, we have 8, 4, 8, 16, 32, 64, and so on, then because of this fact, it's even. If you don't agree with me, ask me. Second case, if n is equal to 2 to the power of anything, and then some odd number, right? So prime 1, k1, prime 2, k2, and then prime r, kr, right? Is this general enough or not? Is this general enough or not? Then, what happens? By multiplicity, phi of n equals phi of individual things, right? Individual things. Phi of p1, k1, phi of pr, kr, and other than 2, all these are odd, right? Primes are all odd except 2, right? Primes are all odd. Can you have even prime other than 2? Let me know if you know. Because this even means 2 is already multiplied, it cannot be prime, right? So other than 2, all odd. Because all these are odd, I don't care what happened to this thing. I don't care. But for instance, pick the first one, then P1, K1 minus P1, K1 minus 1, and so on. So let's not worry about other factors. Only focus on the first odd factor. Then this becomes what? By this, just this factor becomes P1, K1 minus 1, and then P1 minus 1. And this is odd to the power of some number multiplied by odd minus 1, then even, right? Odd to the power of something, and then even. So even is found. Once even is multiplied, the whole thing is even, right? The whole thing is even. So because of this region, this is some number times even, and then some numbers. So it's even. So I proved that phi of n is even when n is greater than 2. N is 1. When n is 1 or 2, it is 1, 1. So we exclude 2 case then. It's even. Any questions? So once we have this strong fact about the multiplicity, we can prove many, many things, right? We can prove many, many things. Then I will follow the textbook order instead of mentioning things on my own. The next thing that I want to show is, I already mentioned this thing before, but I will mention this one more time. Under the same condition as above, under the same condition, so let's say that this is alpha, right? This is alpha, 2 to the power of alpha. Then how can you calculate phi of n? Then phi of n equals phi of 2 to the power of alpha, and then P1, K1, then P R, K, R. These are given. Then, by multiplicity, phi of 2 to the power of alpha, phi of P1, K1, and then phi of PR, KR is the same as above, right? Then, as you can see, it is 2 to the power of alpha minus 2 to the power of alpha minus 1. And then P1 to the power of K1 minus P1 to the power of K1 minus 1 all the way down to PR, KR minus PR, KR minus 1. So, after these things, we can extract the term numbers. We can extract the term numbers. Then I attached phi unintentionally, right? The term numbers can be picked out. Then 2 alpha. Then what remains is 1 minus 1/2. And then if we pick this number, then P1 to the power of K1, and then 1 minus 1 over P1. And then you can do the same thing to this number, PR, KR, then 1 minus 1 over PR. Then, as you can see, we can multiply all these things together, 2 alpha P1, K1, all the way up to PR, KR, and then the remaining thing, right? But this is a little bit bad because assume that 2 factor does not exist, right? So in the real proof, we can delete this thing and then include this thing inside P, right? It can be included inside P, right? Do you follow me or not? So this proof is problematic if 2 factor does not exist. So in the first place, we could remove 2 and then say that n is nothing but just P1 through PR. And then if 2 exists, then we can call P1 equals 2. Do you follow me? This way we can avoid any confusion, right? Assume that 2 doesn't exist at all, then you should not use this thing at all. So only existing thing goes there in the first place, right? This way we can avoid the confusion. I wanted to recycle the previous one, but that was a bad idea, right? If we recycle the one, then we may have this unwanted result, right? Do you follow me? So because of this reason, I will erase these things and then clean the proof. Then it's easier than the previous one. By recycling, I didn't gain anything, right? So in the first place, we could assume that n is equal to this one in the first place. Do you follow me? If 2 doesn't exist, then okay. Anything that happens, first thing is called P1, right? First time, right? Anything that happens in the first position is called P1, and so then we can clean up the proof. And then because of this reason, I will write it. And because of this reason, this number is nothing but what? N, right? So n multiplied by 1 minus P1, and then 1 minus P2, and then 1 minus, even this one could have encounter some objection because, assume that there is only 1 prime. So in this sense, we say, there are enough primes, right? If there are not enough primes, then we can just start at 1 prime. But in any case, it's the idea part, not the rigorous part. But the idea is good enough. In any case, I proved this thing. And unless you have a question, I will continue. The next case is calculating this thing using factorization. So you may pick your own number, then I will use your number to calculate phi. So please pick n. Any n is okay. Any reasonable n is okay. 13. But this is just prime. Then prime is not very exciting. 14. Great. N equals 14. Then 14 equals 2 times 7. So phi of n or phi of 2 times 7, right, equals 14 multiplied by 1 minus 1 over 2, 1 minus 1 over 7. Do you follow me? This is it. Right? Then let's calculate it. 14 multiplied by 1/2, and then 6/7. Then we can cancel out these things, then it is 6. Right? 2 times 7 is 14, so cancel that. So I will pick something that may scare you. For instance, 24 is way harder, right? Then 24 is what? 2 to the power of 3, and then 3, right? 8 times 3 is 24. Then, what should you do? Oh, just write 24, and then 1 minus what? And then 1 minus what? 1 minus what? 1/2. 1 minus what? 1/3. This is it. So once you know these things, you can easily calculate phi of. So let's do it. Then it is 24 multiplied by 1/2 multiplied by 2/3, right? Then it is 8. Now, I will, as I mentioned before, I will factor 2. I will factor 2008. 2008 is 2 cubed multiplied by 251, right? 2000 this year is 2 cubed multiplied by 251. Because I showed you before, I'm using it. Phi of 2008 equals phi of 2 cubed multiplied by 251. This is it, right? This is the factorization of the given number. Then this equals 2008 multiplied by what? 1 minus something, 1 minus something, right? What is it? 1/2, and then 1 minus what? 1 over 2, 1 minus 1 over 251, right? This is it. Then, as we can see, (2008) multiplied by 1/2, and then multiplied by 250 over 251. And as you can see, if you multiply this for 502, right? 502 divides this, right? And the quotient is 4. 4 times 250 is what? 1,000. So millennium, right? So this here is Euler millennium. In any case, I think it's a good idea to continue and then cover the next thing. But before proving Euler's theorem, which is the generalization of Fermat's theorem, I will prove the thing that I mentioned. I said this thing. Prove that if we add phi of d for all divisors of n, right? For all divisors of n, you will get n. So this is the one that you can prove. So let's do it. If you just start with this thing, you will suffer. Why? Because finding divisors is not trivial. Right? Finding divisors is not trivial. So the thing that you need to do is, because phi is multiplicative, we can consider n equal to p to the power of k, or we can replace n by k, right? Replace n by p to the power of k, right? So this is the thing that I will do, right? I will erase and then rewrite it. So replace n by k, p to the power of k. Then what happens? Sum of this thing, p to the power of k, phi of d. Any questions? So I will calculate this thing, and the end result should be equal to what? P to the power of k. Then we are done. So I will write it. What are the divisors of p to the power of k? P to the power of k is divided by 1, right? And then p to the power of k is divided by p. P to the power of k is divided by p squared. P to the power of k is divided by p cubed, and so on, right? If you don't follow me, ask me. So these are possible divisors, right? We are summing over all possible divisors p to the power of k. One is a divisor p squared up to p to the power of k. These are divisors. For general n, finding these things is very difficult, right? Finding these things is almost impossible. But for p to the power of k, as you can see, very straightforward pattern. Then, for each prime power, what can you do? First of all, by definition, p to the power of 1 is 1. Because it's prime, p minus 1. Do you follow me? And because of this, what is it? P squared minus p to the power of 2 minus 1, right? And then because of this, p cubed minus p to the power of 3 minus 1, and all the way up to p to the power of k minus p to the power of k minus 1. Do you follow me? I just used the fact that I mentioned very early. Then, as you can see, we can cancel out this, right? This term and then following term. And then as you can see, we can cancel out this term and then this term. And then you can cancel out this term and then this term. And then you can cancel out, right? So it's a telescopic sum, and then we can cancel out this kind of way, and then all the way up to this. And then in the end, all we get is this thing. So on the exam, when I ask you to prove this thing, all you need to do is proving this, and then by multiplicity, done, right? Right? So let's stop here, and next time I will cover very, very important theorem called generalized Fermat theorem or Euler theorem, which is used in coding in modern days, coding theory.